Alright, let's have a look at the daily challenge problem. Problem 462. Minimize moves to equal array elements 2. So in the previous video, we explained why the final state in this problem will be the media, and we computed the media. Then we computed the absolute deviations from the media to get the result. So here we would like to share a method using binary search idea. So this is just for fun, and also we practiced a number of problems which use binary search idea in a more complex way. So you are encouraged to have a look at that playlist if you have time. So again, let me refresh you the problem. So given an integer array called nums of size m, so return the minimum number of moves required to make all array elements equal. So in one move, we can increment or decrement an element of the array by 1. So in example 1, so we know the final state of this problem is 2. So we are going to increment 1 by 1 unit and decrement 3 by 1 unit. We are going to need 2 moves. So let's directly go to the analysis of the problem. So previously we used the method around the median, and we provide one solution. So actually around this idea we can write different formats of solutions. But for now we would like to practice the binary search idea for fun. So what we want to explain is that in the binary search, how do we do search range shrinkage? So that's our main goal here. So we know actually a priori for this problem, or we have the intuition. There is some state, final state m, such that the sum of the absolute deviations from that number is minimized. So here actually we know, based on previous video or our background, the m is the media of the nums. So here the question we want to ask is, what if we do not know the concept of median? Can we still find the final result effectively? That's the target of this video. So I'm going to copy this functional signature and call it solution v1. And then what I want to do is do a binary search solution. So let's recall that. So in the binary search, basically there are 2 steps, as we mentioned in our previous videos. The first one is define a Boolean function. So this role of the Boolean function is to produce order or monotonicity, which enables us to do binary search. Second is do binary search, or more precisely search range shrinkage. So here we are going to focusing on the second step, the search range shrinkage. And for this we need to quickly define a Boolean function. So let's carry out the procedure. So first I'm going to determine our goal. So let's see the goal. So we have assume we want to find some final state. Let's still call it m. So we want to compute the absolute shrinkage, the absolute deviation of the num element from that m, or the argument m. If we find the best m, the value of this function is what we want. So absolute value of a minus this m. So here I'm going to do sum of these absolute values for a in num. So that's our goal. So but in order to determine a search range shrinkage, we need to define the Boolean function as previously we did. So actually we do not need to specify or explicitly define a Boolean function, but in order to be aligned with the previous video, I'm going to define one. So what I'm going to define is, I call it fulfill. So this is M. Then what I want to do is I want to compare the go function with its neighbor, right, to see if it's good or bad. So what we are going to return is the go if at M is greater or equal than the go at M plus 1. So this is going to give us a order or monotonicity. So next we are going to do the search, right? Let's group this one by step 1. So binary function. So the second step is the binary search and the shrinkage. So that's the part, search and shrinkage, we want to demonstrate through this simple example and just to play with it. So first we want to determine the range. So based on this problem, we want to find the final state of the equal elements, the value, right? So that value obviously should be between the minimum or maximum of this norms. So here I'm going to initialize this low and high to be the minimum of norms and the maximum of norms, right? So if the low and the high are equal, so it means that all the elements in norms are equal, so we do not need any operations or moves to make them equal. So then we're going to do the shrinkage. So that's the part. So as in the standard binary search, we're going to check this condition, right? If low is less than high, we're going to compute a mid, which is half of the way. So if we use low as a reference point, so this is going to be high minus low divided by 2. So low plus this half range. Then we are going to check fulfill. So if fulfill middle, so if this is true, in other words, if fulfill middle is greater or equal than 0, so what does it mean? It means the value at M is greater or equal than the value at M plus 1. So basically it says that we need to search above M. So in this case, I'm going to set this low to be M plus 1. So this is the range shrinkage. Otherwise, I'm going to set the high to be mid, right? So finally, we are going to return the goal. So in this problem, either low or high are okay, but here I'm going to return low. Let's first check if this works, and then we analyze the shrinkage part. So if we test this, it passes the first one, and then let's do a generic case test. It passes the generic case. So here, I guess the point that might be confusing is this search range shrinkage. So for that, let's see a graph. So here is a graph. So roughly, we want to minimize this function, and we know there is some point, actually it's to be the median, which is minimize the whole function. So we have a search range low and high. So this low can be very low because of the range element, the range constraint on the elements in the norms, and this high can be very high, right? So then we're going to define, we're going to compare. So if mid is the goal function we defined is greater or equal than their neighbors, the right neighbors. So if, for example, this is a mid, and this mid is greater than its right neighbors, in other words, mid plus 1, or the fulfill function is true, we're going to search above the middle. So in other words, we're going to search from middle to high in this range. This shrinks this part, right? So we set the low equals mid plus 1. So otherwise, if the mid is in this part and mid the goal has value less or equal than the right neighbor, then we're going to search in this range. So we're going to set high equals middle. So we search from low to mid and we drop this part. So that's the whole idea for this problem. So let's come back to the problem itself. So we the structure is like this. We define the Boolean function and we use the Boolean function to determine to which direction we need to shrink the search space. So that way we achieve the binary search idea. So for this problem itself, so if we know a priori the concept that involved is the median, we do not need to do this. However, if we do not know the final state is going to be the median, we can use this method, the binary search method, to do the search and to get the best the final result. So let's emphasize again, the whole purpose for this video is not solving this specific problem, but to demonstrate a general way of using binary search. There are two key points. One is defining the Boolean function, which plays a role of enabling the binary search. And the second is that we do the shrinkage. But for the shrinkage, actually, it's not trivial. So in the traditional binary search scenario, for example, we search an element in an array. So the binary function and the shrinkage are obvious. But in some of the examples we have practiced, the binary function and the shrinkage can be quite non-trivial. So actually, that's also the elegant part in the latter situations we can use binary search. Sometimes it can give us very good performance and very nice solutions. So I guess that's about it for this video. Thank you very much.